Now let's take a look at example number 3. In this question I want to set up, but not bother to evaluate, a triple integral that could represent the flux of f across sigma, where the vector field f is given by what's listed up here, and sigma is the surface of the solid that is within the elliptical cylinder, 4x squared plus 9y squared is equal to 36, and bounded above by the ellipsoid that's given by the z equals formula, bounded below by the plane where z is equal to 0. You can kind of see I've sketched the solid over here on the side. You can see this kind of elliptical cylinder shape down here at the bottom, and we can also then see this ellipsoid shape that's occurring up at the top. And of course this is cut off when z is equal to 0. So this is the solid that I'm working with. Now again, I have a couple different ways that if I wanted to compute the flux just by itself, I could refer to the surface of this ellipsoid as sigma 1 and kind of this bottom portion, this bottom ellipse, as sigma 2. And to get the total flux, I would have to do the flux through sigma 1 and the flux through sigma 2 and take their sum total. Now of course that becomes a little bit more complicated because I have to go ahead and actually deal with normal vectors on each of those surfaces. I have to go ahead and compute two separate integrals, and it takes a lot of work. And that's of course why this question is going to ask, can I go ahead and set up a triple integral, that is, I want to use the divergence theorem to help me maybe do this question a bit more simply. So we want to go ahead and do this. We're going to assume though that the solid has outward orientation. So again, that means that I'm going to have vectors that are normal to the surface pointing out in this direction, right? So I'm going to have things that are normal to the surface pointing outward. So one thing that I can do then right from the start to try to get ready to use the divergence theorem is to note that sigma itself is the boundary of a solid. So I'll say here, we see that sigma is the boundary of a solid called G, which is built from a bunch of points x, y, z, such that, well, we can see a couple things here. We would need 4x squared plus 9y squared to be less than or equal to 36. Again, that's going to make it so I'm only dealing with points that are on this bottom ellipse or inside of it. And I'm also going to need to have that things are below this ellipsoid. So this z has to be less than or equal to 1/2 times the radical that's given here. So this is my solid of G that I have. So the divergence theorem would tell us, so I'll say here by the divergence theorem tells us that if I want to go ahead and compute the flux, which is given by this, what I would have to go ahead and do instead is to set up my triple integral over G of the divergence of f. Okay, so let's calculate the divergence and see if how difficult this is going to be to work with. So let's see, the divergence is going to be here, starting with my partial with respect to x, looks like 2x, then plus 2y, and finally plus 1. Okay, so if I can go ahead and understand this particular solid and how to set it up, then I might be able to go ahead and figure out the bounds of my triple integral and how to work with this. Okay, so let's see what we got. First things first, I need to set up bounds, and maybe I can start here with like a floor and a ceiling. It seems like that we already know that the value of z is already wedged between 0 and this upper ellipsoid. So this can serve as nice bounds on z. And then I can think about projecting my solid down into the xy plane. So I can say we then project G into the xy plane. And of course, when we do that, we obtain, we'll say, a region D, which is clearly going to be just a bunch of x comma y points, and it's going to be all those points that are inside or on that ellipse. Oops, that should be 36. So there's the region D. Now, this is going to be particularly difficult to describe. Like if this had been a nice circle down here, we would have been ready to go in defining that circle with polar coordinates, set up this integral, and it's no big deal. But this ellipse makes things maybe a little bit more complicated to try to work with. However, we might notice the following. If we let if we let x be equal to 3u, and we let y be equal to 2v, or actually I can go ahead and let's quickly take a look at what happens if I set this up. Sorry, I was trying to figure out the best way to say that. But if I let these two things be equal to these values, then I can see that D would actually become a region that I could define in terms of U's and V's, but notice that it would look like, let's see, I'd have a 3 squared, and then times a 4, I'd have 36 U squareds plus 36 V squareds less than or equal to 36, which of course is equivalent to saying that I would have U's and V's that are now going to need to satisfy that U squared plus V squared is less than or equal to 1. Ultimately, I'm setting up here a change of variables. And the way that change of variables is going to work is, again, it's taking the the ellipse that I have at the beginning, and it's going to modify it. So I'm going to be going ahead and saying that the ellipse that I started with, which maybe looked like this, I'm now going to be able to go ahead, let me see if I can resize that one more time, but I can go ahead and I can change that ellipse using this substitution into a nice circle. And so of course the circle is way easier to try to work with because I can describe it very, very simply with polar coordinates. So again, what I have here is a picture of the region D over on this side, and here I have this kind of updated picture of the region D, which I can describe using these new U and V variables. To distinguish these, I'm going to go ahead and recall this region S. So I have, again, a region S over here. It's a nice unit circle. And I have my region D over here. We've set up a change of variables in this case, like we did with section 4.7 in the last chapter. So I'll write here, to finish this off, that our change of variables implies the transformation T, which takes in U's and V's and spits out X's and Y's. It takes in U's and does 3 times U to get X, and 2V will produce the value of Y. Of course, if that's what we have for our transformation T, then the Jacobian of T is, and I can set this up. My Jacobian here is going to look like, let's see, I'm going to have to do partials with respect to U going across the top, and partials with respect to V going across the bottom. And so when I calculate out my Jacobian, I end up with 6. So using our knowledge of change of variables, I can say that my triple integral, which was over G, and it used to have in it a 2x plus a 2y plus a 1, I now have been able to change slightly. We know that we now have a double integral on the outside that used to be over D, and we had our inner integral, which had our bounds on Z, which was this big mess. The bounds on z were 0 to 1/2 times this gigantic radical. And now, let me continue to write this in here. Plus 2y plus 1. And we had dz and then dA, our remaining area. But with our transformation, we know that we could go ahead and reestablish this as an integral, double integral over s. We could change our bounds here to be in terms of u's and v's. Notice that would give me an upper bound of a square root of 36 minus, remember x again is 3u, so I'm going to get 36u squared minus 36v squared. Down here I'm going to have to change this out. I know that everywhere I see an x I have to put in a 3u, so that's going to be a 6u, and then I'm going to have a 4v plus 1, and this is a dz, a dA, but now with u's and v's. So I've almost completely set this up. I just have to set up this outer integral. I have to understand how I want to integrate over this region of S. Well, if I go kind of back up here to the top, I can see that if I wanted to, I could define S again in polar coordinates. That was the whole goal for doing the transformation in the first place. The ellipse was difficult to work with and the circle's easy. So I can see here that since this is going to be a circle of radius 1, I know that my r goes from 0 to 1, and my theta is going to go from 0 to 2 pi. So these can be bounds that I can use on my outer integral, or outer double integral, and then I can go ahead and just make sure that I transform everything else. So jumping to the final page, I can see here that if I change this integral to go from 0 to 1 and 0 to 2 pi, I can keep the inner integral the same, except I'll have to adjust my upper bound slightly. I'll leave that blank for the moment. I'm going to have to adjust my integrand, and then I know I'm going to have a 6 from my Jacobian, and then an r dz dr d theta, because I have that r from the r dr d theta when I substitute. Now, my upper bound here is also going to have to change, because I have to change this upper bound here into r's. Well, keep in mind, again, that on this picture where I have u's and v's, it must be the case that u is equal to r times the cosine of theta, and v must be equal to r times the sine of theta in this picture, just like I would have normally had x equals r cosine and y equals r sine. Here I just have different variables. Notice that if I go ahead and I plug those sorts of values in, I can change my integrand. So this would give me 6r cosine theta plus 4r sine theta plus 1 as my integrand. Up here I can do something a little bit easier, because I notice that if I factor out this negative 36, I'm going to get u squared plus v squared, and I can simply just replace that with an r squared. So this would be the full transformation. And now I have an integral that's actually ready to tackle this. Now, this is a lot of work, and when the moment you heard that I was going to be doing a change of variables, if that terrifies you, get on board, because for most people, that's a terrifying thing. There's a lot that's going on in this particular question. The thing again to notice is that this was just an option that we could have used when we have this divergence theorem in play. Divergence theorem is just here to help us compute the flux in a different way, and sometimes that way will be more complicated or less complicated than what we started with. Again, it might have even just been easier on this question to just deal with the actual function and the flux itself going through sigma 1. It was a z equals formula, so that might have been easy. And down here it might have been easy to work with that ellipse potentially as well and just add the two fluxes together. Unfortunately, since I have this elliptical shape as this bottom edge, it's really always going to kind of create a small problem. Ellipses are just always difficult to work with, and they usually always require this transformation back to a circle. All right, that problem might take a little bit of time to get used to, and you'll have to re-review a couple times. But in the next video, we'll take a look at example 4 to see one other way that we might be able to try to use this divergence theorem to help us answer some interesting questions.